behave like a, you can say, okay, let me come back to this question again. One second, let me check. Sorry, it got disconnected. And so once again we start from there only. So we have our this rod, and the disk is now going to behave like a point mass, so it is not going to contribute toward the various calculation which we have already discussed. And therefore we can say that our, so first of all we are going to find out our distance d. So this will be our length L and mass will be our m. So it will be point mass, so which can be easily neglected. And once again we know that our time period formula is t is equal to 2 pi, and its square root moment of inertia, and we have our mass total, and this is g times d. So once again we are going to find our d, which is distance of the pivot center of mass of the system from the pivot point. So here d will be equal to our, this will be our mass m, and it will be our L m by 2 plus m, and total will be our m plus capital M. Okay. So here we have to, I think, let me check. Yes, so I think, I'm not sure whether, okay, I just want to repeat one thing more, that previously we, in the first case, we considered that this is our disk, and then we calculated its center of moment of inertia with respect to the center, and then we use the parallel axis theorem. But in this particular case, the disk is behaving like a point mass, so okay, it's already on the its center, so there is no need to find out our, you can say, ICM. So that is the second major difference. And we calculate our d, and the moment of inertia of the rod will be same because nothing is changing there. So we can say I rod will be equal to 1 by 3 and ml square. And now this mass is a point mass, so its moment of inertia about the pivot point, we can say that our I disk about the point P will be equal to our ml square. Here will be no ICM will be there. Therefore, let us call this as I prime in order to differentiate, and this is a d prime and m prime total. So everything will be different. So we have this as IDP. So let us call this as I prime, and this is also our I prime. So we can say our total moment of inertia I prime will be equal to R rod prime plus IDP prime. And we substitute the values we get I prime will be equal to 1 by 3 ml square plus capital ML square. And from here we can take L square as common. So this will be 1 by 3 m plus capital M. And so everything we know, we can just substitute the values. And let us call this as our T prime. So we get our T prime will be equal to our 2 pi, and our I prime was our L square 1 by 3 m plus capital M, and we have here total mass is our m plus m times g, and distance we got this as our L m by 2 plus capital M and divided by m plus capital M. So this m plus m cancel out, and here our, okay, we will keep it as it is so that we can make a comparison also. So we get our T prime is equal to, this is our 2 prime 2 pi, and we have this as our L square 1 by 3 m plus capital M, and this becomes as our GL m by 2 plus capital M. Okay. Now if we make a comparison between T and T prime, comparison T and T prime, and if we look closely, we can say that our I moment of inertia will be that I was our, we used our center of mass, that is our 1 by 2 mr square plus ml square. And we know that our this ml square is equal to our, one second, this IDP is our ml square. Okay, so this is capital. So in this place we can write simply our I prime. So this comes over 1 by 2 mr square plus I prime. Therefore we can say that our I upon, or we can say I is greater than I prime, and we can also say that our I upon m total G D will be greater than I prime m total G D prime, or we can say that our T will be greater than T prime. Okay, so this is basically comparison of their time period. Next question. It states that a solid disk of mass m and radius r is mounted concentrically on a vertical massless shaft connected to a torsional spring that provides a restoring torque tau minus c of theta, where theta is the angular displacement from equilibrium and c is a constant. Assume frictionless bearings and negligible shaft and spring mass. So based on this we have two questions. Show that the disk undergoes SHM and determine its angular frequency. And part B, if disk motion is theta t is equal to theta naught sine omega t, with omega from part A, at time t1 pi by omega, a thin sticky ring of mass capital M and radius r is dropped concentrically onto the disk and it sticks. Find the new angular frequency, and part 2, the new amplitude of the oscillations. So these are the questions that are based on it. So in this case, we are given that we have a solid concentrically, okay, the vertical shaft. So we have a disc which is mounted on a shaft. Okay, so we can assume that this is mounted like this, and to this shaft we have connected a spring. Okay, so suppose this is our spring and it is fixed to somewhere here, okay, and this is our torsional spring which is wound on this, and its torque is restoring torque is given by this particular spring. And so this radius is given as, okay, so we know its mass is capital M and radius is given as capital R. So for part A, restoring torque is given to us, tau is equal to minus C of theta, okay. And we can also find out, write the rotational equation of the motion. You can say our rotational equation of motion, and based on this we can say that our torque tau will be equal to I multiplied by double derivative of theta. And we have a solid disk, and so we can write its moment of inertia will be equal to half mr square. So we simply substitute it and we get, because this tau and this tau, rotational motion, they are going to balance each other. Therefore we can write that our 1/2 mr square, and we have this theta double derivative is equal to minus C times theta, okay, and this is nothing but our equation of our SHM. We can write this as our double derivative plus twice C upon mr square times theta is equal to 0. So we get that our omega will be equal to 2C mr square and its square root. So this is our frequency we are supposed to find out, angular frequency. Okay, for this next part we require time period, so we are going to find out T, and later on we are going to deal with it. So from here we can say our T is equal to 2 pi upon omega, which gives us 2 pi square root of m square upon 2c. Now we come to our part B. And part B states that our at T is equal to pi by omega, a sticky ring is dropped and it sticks to the disc. Okay. So for the part B, the equation is also given that our theta T is our theta naught sine of omega t. Okay. And so at T1 is equal to pi by omega, we can find out the position of our disk, that is at theta 1 will be equal to theta naught, and this comes as our sine of omega, and this is our pi by omega, and omega cancel out, so sine of pi, this will be giving us equal to 0. So it means at this particular time, that is pi by omega, the disk will be going through its equilibrium position. That's why the angle is equal to 0. Therefore, we can say from here that the disk passes through the equilibrium position. Through equilibrium position. And we can find out here its angular velocity. So you can say angular velocity at t1 is equal to omega upon pi. So we simply differentiate it. We get this as single derivative at will be equal to theta naught omega cos of omega t. And this is our theta 1. So we substitute now, sorry, t1. So we substitute our t1. Therefore, we get that our angular velocity at t1 will be equal to theta naught omega, and this comes as cos of omega pi by omega, and here omega and omega cancels out, which comes as cos of pi will be equal to -1. So this will be coming as minus theta naught times omega. So it means at this particular instant, t1 is equal to pi by omega, it is going to have a maximum speed, but opposite to the direction of the restoring torque. That is the purpose, that is the significance of this negative sign. Therefore, from here we can say that so it has maximum speed directed opposite the restoring torque. Restoring torque. Now we come to our sticky ring part. So we have a sticky ring whose mass is given as capital M, radius is R, and lands on a disc. Lands on the disc. And because it is not mentioned in the question, but this entire, the sticky ring is going to fall on the rotating disc, and it is going to stick to the rotating disc, and this is going to happen in the fraction of second. So there will be no external force. So obviously we can say that the angular momentum is conserved. Angular momentum is conserved. So let's find out before. Let's call that collision. So before collision, that is the angular momentum L initial will be equal to our moment of inertia of our disc and our theta prime I initial, that is our omega. Okay. And then we have after collision, that is our L final will be equal to our moment of inertia of the disc plus of the ring, sticky ring, and they will be rotating the same angular. and simply equate them. So we get our I of disk and I of disk plus I of ring, and this is your theta prime, okay, which is nothing but angular velocity. And we are interested in final, so we can just final will be equal to, we have this as our I of disk and denominator will be I of disk plus I of ring, and this is our theta initial, and I of disk is our 1 by 2 mr square and mr square. I of ring is our mr square times first derivative, and this is our first derivative. Okay, we can write here omega also, but I'm just comfortable writing in terms of theta. And this mr square cancels out, and 2 will be LCM, so this will be coming as 1 by 3. Therefore we get this as our first derivative is equal to 1 by 3 theta 1, or we can say our omega final is equal to 1 by 3 omega initial. And we are interested in new angular frequency, and so we can say that our new moment of inertia will be equal to I of disk plus I of ring, which will be giving us half mr square plus mr square giving us 3 by 2 mr square. Therefore, because the spring constant will be same, so we can say our omega nu will be equal to C upon I nu and its square root. So this comes as our C. I nu is our 3 by 2, so this comes as 3 mr square, and this comes as 2c and its square root. And we have our old omega, which is our 2c and 2c upon mr square. Square root. So we can just take their ratio. So we can say our omega nu upon omega will be equal to, this can be written as 2c upon 3 mr square, and this is 2c upon mr square and its square root. So here this 2c mr square goes away. Therefore we get our omega nu will be equal to 1 by square root of 3 times omega. And we can also find out the new amplitude. So we have our new amplitude, and just we know that when the collision takes place, the value of angle of theta was equal to 0. We just found out that our the angle was our 0. So we can say that immediately after collision, our theta is equal to 0 and our angular velocity that is theta prime f will be equal to our 1 by 3, and this is theta initial prime, and in terms of, because we can write this in terms of our theta naught, theta is equal to 0, so this comes as our minus 1 by 3 theta naught times omega. Okay. And I think we have already sorted it out. Yes, we already know, because this is the angular velocity, which is our theta naught by omega minus. And now let's write the equation for SHM. So we can say for SHM after collision, we get this as our theta t is equal to a sine of, and the angular frequency will be our new angular frequency times t, and at t is equal to 0 we get our theta 0 will be equal to 0, and our its first derivative of 0 will be equal to same, and that will be our a omega nu, and derivative will be its cos, and we substitute t is equal to 0, cos 0 will be equal to 1. Okay. And this we can say is equal to our theta dot final. Therefore we can say that our amplitude A will be equal to, we only interested in magnitude of this theta final, and divided by our omega nu, and theta final, one second, we just found out, and we are only interested in magnitude because negative sign is only with respect to direction. So we get this as our 1 by 3 theta naught times w omega, and divided by omega nu, and we already know that the relationship between omega nu and omega, so this gives us 1 by 3 theta naught omega and giving us 1 upon square root of omega upon 3 root omega upon square root of 3. Here omega and omega cancels out, and this comes as our square root of 3 upon 3 times theta naught. And we can rationalize it, so we get our a is equal to root 3 upon 3 times root 3 upon root 3, and this is our theta naught. So 3, this will be 3 and 3 is going to cancel out, so this goes out, so we are left with only 1 by square root of 3 times theta naught. Next question. It states that a thin uniform plank of mass m and length L is pivoted at one end. It is released from rest when it makes an angle of 60 degrees with the vertical. Determine the magnitude and direction of the force exerted on the pivot when the plank reaches the horizontal position. So this is comparatively easy. So first of all, we are given that we have a rod. We have a suppose this is a wall, and to this wall we have a plank which is pivoted, something like this, and it is making an angle of 60 degree with the vertical. And when it is released, so the final position is said to be that this plank is horizontal. Okay. So the plank is at this position, and for this position we have to find out the magnitude or direction of the force exerted at the pivot. Okay. That is at point P. And so there will be a mg at the center of mass here, and that will be also here same mg at a distance of L by 2. So for that we are going to use our energy conservation in order to find out our angular, and then we move forward. So conservation of energy conservation. Energy conservation, and for energy conservation we are interested in, okay, so we start with our first of all the moment of inertia. So we can say our moment of inertia about the pivot will be equal to I, and that is 1 by 3, because the pivot point is at the end, 1 by 3, and this is ml square, and this is 60, but for the time being let us assume this is a theta. We can later substitute this as 60. So we can say that initial potential energy and this we are going to take as y-axis, and this will be our x-axis, y. Okay. And sorry, I forgot, this point is with respect to x-axis. This is our, so pivot point we are going to take as 0. Okay, taking pivot as reference. Taking pivot as reference, y is equal to 0. Therefore we can get that our u of I will be equal to our mg L by 2, and this is our cos of theta. Theta is our 60 degree, so we get this as our mg, and okay, in this case I forgot to, height we have taken, that's why because this is our mg and this height is our going to gives us the potential energy of our center of mass. So ideally this will be something like this. So this is point P, and let us call this as our point C, and this point is our R. So this is our R, and this is our height h of our center of mass. Okay. So we get this as our mg L by 2 and cos of 60, and cos of 60 is 1 by 2, so this comes as our mg L by 4, and final position potential energy, and when the rod is horizontal, our angle of theta will be equal to 90 degree. And therefore we can say that YCM will be equal to 0. Okay, let me write it otherwise. The height of the pivot, you can say that our theta is equal to 90 degree, or we can say that our center of mass is at L by 2 above pivot. So height from pivot, whichever YCM, will be equal to 0, because this was our, now the plank is at the horizontal position, so therefore its YCM coordinate will be equal to 0, because this is the pivot point and this is our MG, and we are also assumed that this is our X and we have this as our Y. Therefore its final potential energy, you can say our UF will be equal to 0. Now we can use our conservation of energy. Conservation of energy, initial, U final. Okay. And okay, I forgot to mention one thing here, that our the potential energy will equal to 0, but it is going to have a energy because of the rotation. Okay, so because initially it is in this position, so it is going to rotate in this direction. So we can say it's rotational energy, which we can say as our K of F will be equal to half I omega square. And this will be our, so final energy will be equal to our U of F plus K of F. Okay, it is rotating about angular omega, angular speed omega. Therefore U of I is our mg L square by 4 is equal to 0 plus 1 by 2 I omega square, and I we already know is our 1 by 3 ml square times omega square. So here this m square ml square cancels out, so this 4 also goes by 2, so we are left with g by 2 is equal to omega square by